Hello and welcome to another demonstration video for INB382. This one here is a little different. I'm not running a Unity demo, I'm actually running a Java demo about radiosity from Brown University, put together by Andre van Dam's research team there. The reason why I run this is because it's a really nice little demo that enables people to gain some insight into some of the fundamental factors in radiosity. And in particular, it shows you differences between gathering and shooting, the use of Guru shading to make the lighting look subtle, and just the understanding via the animations with the arrow how light is actually shot into the scene. So what we have here, this is a little Java app. Refer to the lecture in details about, you've got to set up Java 1.6 because it's a very old app. But notwithstanding that, it's a very fine little demonstration. So here we have the sort of Cornell box scenario. Green wall, red wall, white floor, and grey background, I guess, and an emissive plate at this height in the scene. So it's this sort of standard radiosity solution box. And what we see here is the grid showing the level of detail for the let me just put that back in again. So the level of detail of the subdivision of the meshes. So understand that your radiosity solution is essentially a finite element analysis approach, and you subdivide your polygons up into chunks and you calculate for that chunk. And as you have more and more finely detailed chunks, turn the grid on again, then you'll get a better solution. So this is the maximum. Here's a division of 5 by 5 of each of the quads for the sides. It's just, you could have it better and then get a better solution. But a lot of the time, there's a point where humans do not see much of a difference. Therefore, there's no purpose in continuing this solution. It converges nicely based upon human subjective perception. And that's all you care about for such graphics systems. So you'll see here is the form factor matrix visualization with the rows and columns. The rows representing effectively a dominant form for gathering the rays across the rows. But when you run the shooting approach, it goes down each column. So effectively it picks the brightest column in the scene and finds the brightest patch and then shoots that to the other columns in the solution. And you'll see that happen in the animation. So without further ado, you just run it. So once you get up and running, you hit play. And you see here what we've got is a gathering solution. This means that every polygon in the scene, you iterate through each polygon and you gather from every other polygon its contribution recursively to the radiosity solution. And as you can see, it's a little bit slow. It's inefficient because you're sampling a lot of patches that are not contributing much to the actual radiosity solution in that location. So this is the gathering approach, and we talk about this symmetry with regards to the transport of light in the scene that enables us to exploit a shooting approach. So let's not let that go. Actually, what I should show here, see the little dot moving across there. You can see how going through the form factor matrix, it's picking up the elements in the scene that are visible at that point, of course, except for itself. So the leading diagonal is left blank. And what we see here is that it's going through the rows, sampling the contributions from each of the rows. And so that's how it's adding to each of the points here. But as you can see, the floor is sort of computed, and that's great. And so we've converged, but it's taken a long time to compute this. So what we then do is we'll stop that and we'll run it with a shooting approach. This is where the lights are shot into the scene and you iterate down the columns inside the form factor matrix. And note, this solution visually converges much quicker and therefore is much faster to compute. So when you look at on the real-time systems that are, say, used in Unity, they will use a shooting approach. The light sources propagate their light into the scene according to a form factor approximation, which I believe in Unity is a quite complex polygonal data structure for showing where light propagates in the scene. And there'll be more details on that in the lecture. Most of it's hidden though, because of course it's commercial work by geomerics from Cambridge University. But we can see here a very simplified form of this. And as we can see, we've shot light into the scene, and then we take the next brightest patch in the scene from that iteration and shoot its contribution to the rest of the scene. So you can see there, it's iterating through shooting light from there, and then it goes to the next brightest one. So it just moves its way across the columns, going down the rows and shooting to each patch that is visible from that point, except for itself. And this means that, as you can see, very quickly, you get a feel for the visual quality of the scene early on, as compared to the gathering method, which was still working its way across the floor, because it had to gather everything from every other source in the room. But here, we can quickly shoot the light from the emissive source at the top here down to the rest of the floor, and then it bounces around the room. So we're doing the other bounces now. And we end up with something that's starting to look quite realistic. So if we get rid of the grid, as you can see there, we get this quite nice subtle shading. And eventually, once it sort of iterates through a few of the, once it gets off the floor and starts bouncing light off the walls, because they're less bright, we should eventually see, and in fact I can control this, so I'm just going to bump it forward. And we're now starting to push light from the walls into the scene, and lo and behold, starting to see reds and greens appear on the floor down below. Now, of course, that's still not quite complete as a solution, but it's converged visually quicker. Now we can see now that the subtlety of the bleeds is starting to manifest, and that gives us a much more shall we say, quicker solution to this, but in some ways less exact. So you can stop at probably 2 bounces, and you will end up with a scene that's quite realistic. This means that it starts to come into the scope with some nice spatial data structures and so forth, which I talk about in the final lecture. This enables the solution to very quickly converge, and we now have some real-time solutions for static objects in Unity, along with a few other fudge factors. So this is just a handy little demo. I suggest you use it and play with it. I have in my lecture notes, you'll see the results, sorry, not the results, the URL for this demo. And again, I note that you have to set it up with Java 1.6. So this is a bit of a problem because I've had to download bits and pieces onto the Mac from various addresses. But I really like this demo because it clearly shows how the shooting process works. And so imagine this for a much more complex scene with allowing for occlusion and so forth via the form factor matrix, and then you get quite realistic lighting being simulated in these systems. So I'll push this across to the end, and the simulation comes to the end here, and then we have, oops, I've killed it off, but it doesn't matter, I can shoot it out again very quickly. We can take it to the end, and here we have the final radiosity solution for this sort of trivial box scene. Thank you very much, that's the end of the video.